Hello, my name is Vihan Akshay, and I've been working on building algorithms for unsupervised behavior recognition in mice using deep reinforcement learning. This is being done under the guidance of Professor B. Ravindran from CS Department, IIT Madras, and it is also a collaborative project with Jackson Laboratories from the US. Okay, so the motivation of the project. With time, animals have evolved to have a complex behavioral repertoire to support their life systems. And arguably, the most explicit representation of these behaviors is a sequence of physical movements. So that's basically the easiest to observe for us human beings. And these physical movements are inherently generated by a combination of genes, metabolism, neural signaling, and all that. And the motivation here is to replicate these behaviors by training our own agent, believing that this will aid us in understanding the biological mechanisms inherently present better and also the principles behind generation of these behavioral sequences. Okay, so let's just talk about an example. Um, if we observe a lot of the street dogs, we know that some of them are friendly, meanwhile the others aren't. We know this because we observe how they behave for a considerable amount of time, and we try to predict their behavior. Similar to that, when it comes into animals, we can have human beings to actually watch videos and come up with these behaviors, but it has a couple downsides. First, being it is very labor intensive, you'll need people to watch videos for a long time to come up with meaningful observations, and there could definitely be many missed behaviors that are actually present but we don't observe. So what we do is we try to do this process of identifying behaviors in an unsupervised manner with the help of computers. So this project objective basically is being an attempt on behavior discovery on mice, specifically the Jackson dataset that we have, in an unsupervised manner. And to do this, we use something called options framework in hierarchical reinforcement learning, which we'll discuss about later in the slide. We also want to improve the existing pose estimation models. These models are basically used where the videos that we have, we run these models to get key points, let's just say joins and positions of the mice. Okay, so this is a overview of reinforcement learning. So here, what we have is we have an agent which takes an action that alters the environment, which informs the agent of a state and the reward. So based on the new state, it will again keep taking action. So it keeps changing. It's like you start from state S0 and then you take an action, you go to the next state. But to evaluate how good an action is, you get a reward. The goal of this agent is to learn a policy pi. So by policy, I mean a policy is something that looks at the state and determines what action to take. For example, if you're hungry, you know that you need to eat. But if when you're hungry, if you play, it's definitely not going to help you biologically. So that way, that is the policy. It tells you what action to take depending on the state you are in. So the goal for the agent is to train a policy pi which picks actions that maximizes the total reward that you get, total cumulative reward, which is called the return. So we'll also talk about something called behavioral cloning, which given the trajectories we want to train the agent. For example, let's just say that Federer plays a certain way, plays tennis a certain way, and I want to play similarly. So what I do is I try to watch his videos and then I try to see how he plays and I try to imitate him. So that's behavioral cloning. Okay, now we move down to the hierarchical structure. We spoke about these actions, physical actions taken by animals, right? So animals exhibit these common reproducible movements of their physical body, and these behavioral traits on a higher level can be described as being constructed from primitive actions, and this is also supported by behavioral recognition literature. So for instance, I can say that let me say that movement of my body joints is the primitive actions, and every time I move my hand, I pick something up, I move close to my mouth and I eat. So this sequence happens very often because this is nothing but eating. So instead of looking at everything at a primitive level of basic actions, we define higher actions. Instead of just saying move your right leg, move your left leg, move your right arm, move your left arm, we try to have these higher level abstractions like eating, sleeping, which are basically composed of smaller trajectories of actions. So that way we have one level of hierarchy. And if we see biologically, there are papers which show that the actions that we take have a lot of hierarchies. So basically, that's what's written in the slides. Sequences of actions in biology are hierarchical in nature. So if we want to model our project like our use case in this hierarchical structure, then we say that the mouse is the agent and primitive movements of hands and legs are actions. Then let's just say that there are the sequence of actions which result in the mouse going to a corner of the arena and always sleeping. That just says that the mouse is sad or is tired. So these sequence of actions, these the mouse being tired, these behaviors are nothing but discovered options, because options are sequence of actions as we discussed before. This is what we define as options. So this is what we go. This is the goal for us to find. So from video data, we want to discover these options, these sequences of actions, and we have option discovery algorithms. Now, if we look at the project pipeline, so first, just as we had discussed, so we have this video data, huge amounts of video data, and then we run this video data into some post estimator, which tells us where these key points are. To put it all into a mathematical sense, rather than just people watching videos, to make it more mathematical, we use post estimators to tell us coordinates of where joints are and what the joint angles are. So these coordinates that we have, we do a little of pre-processing and then we generate trajectories such that this finally becomes meaningful state representations for a reinforcement learning problem. So what happens is, let's just say that I have 2 minutes of video data of a mouse moving around. So if I first run my post estimator, I get these key points and I get like a trajectory of key points, which I then do some pre-processing, and then I generate the trajectories of state action, state action, state action, state. So it starts from this 0 comma 0, and then it takes an action of 1 comma 0, and then it goes to 1 comma 0. It doesn't necessarily mean it's just 2D coordinates, just to give you some example. But then this is what we're trying to do after the post estimation part, and then we push it into the reinforcement learning thing. Going back to the previous slide, we have these, again, if you see here, we have the mouse agent, we have these actions. So these trajectories that we generate here is what we use to identify this hierarchical structure. Now let's just talk about the post estimator that we use. So currently what's being used is the video that we have. It obviously splits it into images, and then each of these images goes into this convolutions, and then they have this pre-trained neural network which gives you the key points here. If you see the image, you can see these 12 key points on the mouse. So we get coordinates of these key points. This model was trained with some data, but the model is good obviously, and it's being used for a lot of other experiments that they run. But for running some complex algorithm like the hierarchical reinforcement learning option discovery algorithm, like behavior discovery algorithm, it is definitely sure that if we improve the performance of the model, naturally the behaviors that we are going to observe are also going to be better. So to do that, what we're doing is so here better state representations obviously mean better behaviors observed. So how can this be improved? The first thing is to generate more training data, right? That's the obvious answer. So to go there, what we did was we simulated the whole thing on Blender. So Blender is basically a 3D render environment. So how we did was we replicated the whole JAX environment, like whatever the environment was in JAX that they took videos with. We replicated the whole thing on Blender, and fortunately we were able to find an open source mouse model which we can completely control, including the whiskers, like the joints and all of that. Until the whiskers, he has so much control, and we can place it wherever we want. The advantage of this is I can place the mouse wherever I want, and I can get the render. So that way I have the image and the 2D coordinates. So that's basically the training data that I'll need for my post estimator. So I can generate how much ever training data that I want. So let's just call this renders, okay, render training data or synthetic data. That's what we'll call it here. But the issue is, so if you see in this slide, to the top left, you can see a simulated image that we obtained from Blender, and on the top right, we can see the real image. And we can see that these images are pretty far. The gap is huge. So we want to define a function or something new, some program that will convert this simulated image into a real image. That is the goal. And to do that, we ideally would want some encoder decoder thing. If you look at the image below, so this is an example this is a paper called Pix to Pix, and a concept where they use a encoder decoder training model, which takes in set A, which is the input image here, and it tries to make it look as similar to set B, but following however set A looks. So that's the use case is extremely similar to what we want, right? So we have simulated image, that is nothing but input image, and we have real image, which is the ground truth, and we want predicted image, which is basically simulated image tried to transformed into being as close to the real image. So this is what we want. This is how we're going to bridge the gap of real to simulation. So this becomes a new post estimation stack. So we have video feed. If you look below, we have video feed that goes into model A, which produces 2D key points. And then we have model B, which takes in 2D key points and it produces 3D key points, which is then used by our RL module. So how do we train these models, model A, model B? So from blended, we have the simulated data, which takes in images, 2D coordinates and 3D coordinates, which produces them, sorry. And so for training model data, this concept is inspired by one of Professor Ravindran's work, which talks about how they have this webcam data and they have high quality traffic data. Training a model on one of them and testing it on the other isn't going to work well. So what they did was they trained it on their webcam data, but then they kept injecting data from high resolution cameras, and it seemed that the model generalized better. So similar to that, we're going to train it on Jack's dataset and put in these simulated data to train model A better. And for model B, we feel that 3D coordinates for behavior recognition and all of that might work better, would probably work better in comparison to just using 2D coordinates. So all these 2D and 3D coordinates that we obtain from our blender, we are going to use the same thing to train our model B. So coming to next steps, the first Jan and Feb month, the plan is to complete the automation of Blender data. Right now we're able to obtain it, but we haven't finished the Python integration and then implementing, like obtaining a lot of data. So we're going to automate that, and we're also going to check out variations of fixed to pix and finalize it. And we also wish to complete model A by this end of February. The next phase, Feb to March, is where we incorporate. So instead of just training a linear model for model B right here, for model B to go from 2D to 3D, we also wish to bring in some of the mouse structure, and we wish to train model B based on that. And then we can push it to hierarchical reinforcement learning and finish everything. So basically the whole structure, the whole workflow. And then April and May would just be wrapping up, where we check out other experiments and then we try out different state representations. For the mice, one state can be all the key points, or another state representation can be link lengths and link angles, like on general robotics notation. So something like that we can do, and the evaluation of trajectories. So however we train this agent, so this agent is supposed to replicate mice. So once we train that agent, we try to put these coordinates that the agent predicts onto a mice, and we can see if it is actually something that replicates well, that scales well for any mice that we see. So this is the goal, and this is the next steps for the project. This is a quick presentation of the work that I've done in my previous semester. Thank you.